Lecture 8, Part 1, Going in Circles, Uniform Circular Motion. The box represents a car. The dot represents, say, an object on a smooth dashboard or a person in the car. The car is on a road, taking a turn around the bend of the road. We see the car driving on the road, taking the turn, and the object drifts to the passenger side across the smooth dashboard. The same as a person not wearing a seatbelt will be pushed to the outside of the curve when taking a turn, or you will feel a push to the outside of the turn if you don't wear your seatbelt. You're not really pushed to the outside of the curve. The object is not really being pushed as it's drifting across a smooth dashboard as you take a turn. So why do you feel pushed to the outside of a curve? Or why does an object drift to the outside of a curve when rounding a curve in a car? Let's look at the animation again, this time following the object. And we see the object takes a straight line path as the car takes a curve. The car, following its curved motion, is taking a different motion, a different path than the object that's drifting to the one side of the box to the other, to the outside of the box. The object follows a straight line path. The object is obeying Newton's first law. It's staying in a straight line, continuing its motion, unchanged unless a force is applied. The force from the outside, the passenger side of the car, unless there's a force on the dashboard from a rough dashboard or a force of a seatbelt, the object won't get pushed until it hits the outside edge of the car, the passenger side. A force is needed to change motion. Without it, the object will keep on going in a straight line, which will make it appear as if the object is moving, being forced to the outside of the car. But it's not. It's simply going in the last direction of motion it had, as the car is turning. Unless an object is forced to turn, it will keep going in a straight line. The seatbelt or a rough surface will cause an object to turn with the car. Without it, it'll go in a straight line towards the passenger side to the outside of the curve. It appears as if there's a force, so we call it a false or pseudo force. Now let's study the motion, the curve motion. We know how to describe a curve from mathematics. The length of the curve, s, relates to the radii of the curve. If the curve is a full circle, and r is our radius and theta is our angle, relating to the curve's length, the path s, to the radius. A full path around the circle would be 2 pi times the radius, or pi times the diameter. V is the velocity vector representing an object going in circular motion. And omega is the new concept representing something that's going as rotating in circular motion. So our velocity is the velocity of the object, like we just saw, that's trying to go in a straight line. And omega is what we'll call a rotational speed, or angular speed, or angular velocity. We know how to relate distance to angle, or distance to the radii. The distance s of the path of the curve relates to the radius, or half the diameter, times the change in angle, theta. The velocity vector pointing tangent to this path, tangent to the curve s, tangent to the circle, relates to the radius, times it by the angular velocity, omega. We can see this because the derivative with respect to time of s, the distance, is a velocity. The velocity is the derivative with respect to time of s. The derivative with respect to time on the left and the derivative with respect to time on the right means we change the angle in time. A changing angle in time, or an angular speed, is omega, or angular velocity. Here we're seeing 2 reflectors on a bicycle wheel. Reflector 1 is closer to the center of rotation, or reflector 2 is farther towards the edge. Reflectors on a moving bike wheel, one reflector is 3 times, reflector 2, is 3 times the distance from the center of rotation. When the bike wheel moves, the reflectors are attached to the spokes, the lines. So their distance from 1 to 2 remains fixed, and they both sweep or they both rotate as the wheel rotates, attached to the spoke. So 1 sweeps a small distance and 2 sweeps a larger distance, but they both sweep the same angle as the wheel rotates. Sweeping the same angle in the same time is an angular speed or an angular velocity. That's omega. Reflector 1 has an angular velocity omega 1. Reflector 2 has an angular velocity omega 2. But they have the same angular velocity because they both sweep the same angle. They're attached to the spoke. They both sweep the same angle in the same time. The tangential velocities, though, the velocities along the path, their curve S, will differ. V1 divided by R1, the tangential velocity V1 divided by the radius 1, is equal to V2 divided by R2. Why? Because omega 1 is equal to V1 over R1. This comes from the previous relationship from the last slide, where R times omega is equal to V. Thus, omega 1 is equal to the ratio of V1 over R1. As that equals omega 2, that equals V2 over R2. Or rearranging, the ratio of the radii is opposite the ratio of the velocities. So, the object, the reflector that's 3 times as far away, has to have 3 times the tangential velocity to sweep 3 times the distance, 3 times the curve, in the same time. Angular acceleration is the change in omega with respect to time. How quickly the angular speed of the angular velocity is changing. The rate of change of angular velocity is angular acceleration, given the symbol Greek letter alpha instead of a. So we have acceleration, tangential, and angular acceleration, alpha. If the angular speed, omega initial, is different than omega final, then omega has changed. The dots on the wheel show us that the wheel is rotating faster and faster. The displacement of the dots is increasing over time. Therefore, the wheel is increasing its rotation. It's increasing its omega. Delta omega is not 0. It's changing with time as the wheel is rotating faster. Thus, we have an angular acceleration from their change of angular speed, omega. Again, S, the length of the curve, relates to radius times angle, such as the full length of a circle, S, is 2 pi, the full angular swept theta, times r. 2 pi r equals S. The derivative of S, the derivative with respect to time, is velocity. The velocity tangential along the curve. The derivative with respect to time of theta is omega. So velocity is r times omega. The derivative of that equation, derivative of velocity is acceleration. The derivative of omega is angular acceleration. So acceleration relates to angular acceleration by the radius. Velocity relates to angular velocity by the radius. And distance relates to angular distance or angle by the radius. So our kinematic equations, we're familiar with how to relate distance to velocity and time, and how to relate distance to velocity if there's an acceleration, our old kinematic equation. We can relate angular distance to angular velocity and angular acceleration in exactly the same manner. Instead, we substitute in distance for theta, velocity for angular velocity omega, and acceleration for angular acceleration alpha. The sign of the angular velocity omega and the angular acceleration alpha is, by convention, if something is rotating CCW counterclockwise, then that's a omega greater than 0, a positive angular velocity. Omega is positive if the rotation is counterclockwise by convention. If the counterclockwise rotation is gaining speed, if the counterclockwise rotation omega is increasing, then alpha is also greater than 0. Just as acceleration and velocity, if they have the same sign, the object is speeding up. If omega and alpha have the same sign, the object is speeding up. And it's speeding up counterclockwise, it's a positive omega and therefore a positive alpha. If omega and alpha have opposite signs, if they're antiparallel, then something is slowing down. Just as velocity and acceleration are antiparallel, the object is slowing down. So if the object is going counterclockwise and slowing, omega is positive because it's going counterclockwise, and alpha is negative because it's slowing. The opposite cases are true. Uniform circular motion. Now that we know the kinematics, let's look at an object going in circular motion and to see the causes of this. For an object moving in a circle, the acceleration turns out to be given by this simple relationship. The acceleration relates to the tangential velocity v squared divided by the radius. But we know v is r times omega. So v squared is r squared omega squared divided by r, or the acceleration for something in circular motion is v squared over r, which is omega squared times r. Whether it's a ball, a particle, a ball on a string, or even a planet going around a star. Looking at our diagram, we have v for tangential velocity, and the acceleration is always perpendicular. Why is this acceleration perpendicular? This is the acceleration representing the change in motion, to keep it in a circle. If the acceleration has a component parallel or antiparallel to the velocity, it represents slowing down or speeding up. Uniform circular motion means the speed is constant. That's the uniform in the circular motion. Circular motion with constant speed. Thus, the acceleration has to be perpendicular. Otherwise, it'd be pointing with or against the motion, speeding up or slowing it down. Because the speed is constant, the magnitude of the velocity is constant, the relationship for distance divided by time, or average velocity, is also r only constant velocity. The full distance around a circle is the circumference. The time around a circle is called 1 period. So the distance divided by time would be 1 circumference divided by 1 period to find the velocity, the speed, in uniform circular motion. So 2 pi r divided by capital T, the period, is the velocity or the speed of uniform circular motion. A useful equation. You know that a force is always changing something's velocity, but it doesn't always mean it changes its speed. If the speed changes, there's a force having a component with or against the direction of motion, then the velocity changes. But it's not necessarily the other way around. Velocity changing doesn't mean the speed is necessarily changing. Change in velocity can also mean a change in direction. For an object to follow a curved path, a force has to be applied, regardless of any speed is changing. You have to force an object to change its direction. That was the idea of the animation in the first slide. To make a golf ball go past obstacles in a miniature golf course, you have to hit the golf ball to deflect it, to make it change its direction. So here a golf ball is going around an obstacle, the lighthouse. To make the golf ball without any extra spin go around the lighthouse, you'll have to hit it a few times to make it follow the curved path shown. If you just want the golf ball to change direction, then hit the golf ball perpendicular to its motion. That way it'll just change direction without speeding up or slowing down. It'll be forced simply to change direction, change the velocity with a directional change, not a speed change. Hitting it more often will make the golf ball change its direction more often. The more often you hit the golf ball, the closer the path of the golf ball will follow a smooth curve. How will it follow a smooth curve? By hitting it continuously. So force is needed all the time for an object to follow a smooth curve. A continuous force is needed for an object to follow a smooth curve. Another example would be a car going around a circular racetrack or a circular road. The road pushes on the car. The tires pushing on the road means the road pushes back on the tires, as long as there's friction, so that the car can make a turn. Here's our car making a turn. You drive around a curved road successfully by following the speed limit. To stay on the curved road, your friend in an identical car traveling twice as fast would need to push on the car. The road would need to push on the car just as much if the car is going twice as fast. The road, the force of friction, would have to be twice as much if the car is going twice as fast to make the same curve. If the car is making the same curve but going twice as fast, the road, the friction needs to be 4 times as much, or half as much, or not at all, because roads don't push. Well, the force of friction, the road pushing on the car, is making a turn. The force of friction perpendicular to the direction of the car will make the car simply turn. If the car goes twice as fast, the road needs to push more. How much harder does it have to push? Well, it's going twice as fast, so it'll have to push more. In fact, it'll have to push twice as fast, twice as hard for going twice as fast. How much more often is the push? Well, the car will make the full circle, the full lap, in half the time if it's going twice as fast. So the road will have to push more often. If it goes twice as fast, the road has to push twice as often and twice as hard. Twice as often and twice as hard means the road has to push 2 times 2, or 4 times as much, to push twice as often and twice as hard for a car going twice as fast around the curve. So if you take a curved road at twice the speed, you need 4 times the force of the road, or 4 times the friction. This is why it's dangerous to exceed the speed limits, or not to go slowly on a curve. Their average force, then, is equal to mv squared over r. Double the velocity, or double the speed, since it goes to the square of the velocity. Double the speed gets you 4 times the force. Triple the speed, 9 times the force. 4 times the speed, 16 times the friction is needed, etc. Here we have 2 racetracks, a large racetrack and a smaller racetrack. The smaller racetrack is half the size of the large racetrack. So 2 cars are traveling at the same speed, but one is on a track of half the radius. For the car on the inside track, how much more is the force from the road on the car? The car on the inside track, going at the same speed, will need twice or 4 times the friction, the force of the road on the car, or 8 times or 16 times the friction, or half. Well, if it's taking this curve on a road that's half the size, it's taking a sharper curve, so it needs more friction, more push from the road to take the sharper curve. How much more? The curve is in a sense happening, or it's curving twice as much to make a circle a half the size. So there's less time to make the less gradual, sharper turn. The shorter bend takes half the time, so the force is applied twice as much. If the force is applied twice as often, you'll need twice the force. So if the force is strong and the time is short, there will be an abrupt turn. Again, this is the turning force. It keeps the object turning. It's forcing it to change direction. We don't need a force to keep an object moving. So our average force is equal to mv squared over r. Over r means if the radius, the diameter of this track, is half the size, then divided by r over 2 gives us twice the force. Force is needed twice as often for the sharper turn. So the velocities, the tangential velocities around a circular path, are half of the description of what's needed for uniform circular motion. If we keep a record of all the velocity vectors around a circle and look at the initial changes, the initial velocities to the final velocities, and the changes between initial velocity to final velocity, if we did it really carefully, we'd see v initial plus delta v to create the next v final. The delta v, the change in velocity, always points towards the center of a circle or center of a curve. Thus, the change of velocity, the acceleration, the force needed by Newton's second law, points to the center of a curve. A force in the radial direction, any force whose direction is pointing towards the center of the curve, the radial force, the centripetal force, and vt, tangential velocity, is all that is needed for uniform circular motion. Uniform circular motion is completely described with a tangential velocity and a force perpendicular to the tangent or along the direction of the radius towards the center or centripetal direction. A radial force or centripetal force is not a special force. It's just any force or a net force pointing in the direction of the center of the curve. Continue on to Lecture 8b for non-uniform circular motion.